So welcome students again in your topic chemical energetic from physical chemistry. In today's lecture, we will discuss about the entropy and the third law of thermodynamics. So what is entropy? Okay, first thing, what is entropy? As we know that this is one of the thermodynamic property or one of the thermodynamic term, which is very important term in thermodynamics. So what is entropy? According to second law of thermodynamics, heat cannot be completely converted into work. As we know that because some part of the heat absorbed will be lost in some other works instead of complete work done because Q is not equal to W all the way. Some amount of heat is not available to do work. That's why it cannot be converted completely into work. Clausius invented a term entropy, which is indicated by the symbol S, which is a measure of such unavailable part of energy. For example, energy may be in the form of heat to do the work. So let us consider a gas filled in a cylinder fitted with a piston. Okay, so this is consider a piston. Consider a container in which a gas is filled and which is stopped by a piston. When heat is absorbed by the gas, then the kinetic energy of gas molecules will be increased and the gas molecules move faster. Then these gas molecules collide with each other. Consider these are gas molecules. When they get the heat, they will collide with each other. They will collide with the walls of container and again they will collide with the piston, okay, and they will push the piston upper side. Okay, that means the expansion of gas will take place as we will provide the heat. In these three types of collisions, only the third type of collision, that means the molecules will when which molecules collides with the piston will result into expansion of gas, but the other two collisions, that is collision with each other and collision with the walls of container, will not able to expand the gas. That means they are dissipating the energy in collision with each other and collision with the container and actual work done. In this case, the actual work done is the expansion of gas. But in this, we can see that only the collisions with the piston will result into expansion of gas. Therefore, the work due to expansion is not exactly equivalent to the amount of heat absorbed. Some heat goes waste only due to random motion of the gas. So, thus the randomness can be correlated with the unavailable energy, which is called as entropy. So, entropy is a measure of randomness of a molecular system. Okay, so randomness means what? The movement, okay, or collisions, movement of gas molecules in any direction. That means upon absorbing heat, they will collide with each other, collide with the container, collide with the piston. Okay, whatever maybe their movement is called as randomness. So entropy is nothing but the measure of such randomness of molecular system. In brief, it can be summarized as entropy is a measure of unavailable part of energy to do the work and order and disorder of the system. More the disorder, higher will be the entropy. It may be defined as the thermal property of the substance which remains constant during an adiabatic change in thermodynamic words. Okay, it is mathematically defined as the ratio of heat change to the temperature at which heat change occurs. Okay, that means it can be indicated as the ratio of heat change, that is dq reversible, to the temperature at which heat change occurs. That is T indicates the temperature and dq indicates the heat change. And the change in entropy ds is given by dq reversible by the T. dq reversible indicates heat absorbed by a system in an infinitesimal reversible process. T is the absolute temperature in kelvins. Got the point? Okay. So the small change in entropy is given by small change in the heat uh, conversion or absorption, small change in the heat at particular temperature. The entropy change from state 1 to state 2 is given by the integral, that is sum of all such terms dq by t. So generally we cannot measure the absolute entropy at a particular temperature and particular time, okay, or particular state. We can measure the entropy at state 1 and state 2, that means initial state and final state only. Between between the process we cannot measure the entropy or we cannot measure any thermodynamic properties. So entropy change can be determined by integration of this term, that is delta S is equal to S2 minus S1 is equal to dq reversible by the t, integration of dq by t. For an isothermal reversible process, the integral can be evaluated as delta S is equal to q reversible by the t. It's dq. All these dq terms will be nothing but total heat absorption. Okay. The value of delta S depends only on the initial and final states of the system and not on the path. Hence, entropy is a state function. Its unit of entropy is joule per Kelvin per mole. Now let us see what is physical significance. What are physical significance of entropy? That is use of entropy. Why it is important? Entropy as a measure of order and disorder. Spontaneous processes are always accompanied by an increase in the disorder or randomness or chaos in the system. So what is entropy? You can understand from this diagram. There is solid, liquid and gas. As we know that in solid, all the molecules or atoms are perfectly arranged. That is, all these atoms or molecules are in well ordered system. In liquid, they are random. That means there is no any order. Okay, only very less limitations for movement of these molecules in the liquid. Okay, that means we don't have that means we have less control on this molecules, movement of molecules, whereas in gases we don't have any control on the movement of molecules. That means the higher randomness will be observed in gas. As we know that water can exist in two forms, if we consider two forms, solid and liquid. In ice, the molecules are arranged in an orderly way with the molecule in a fixed position as like a crystal. Melting of ice is a spontaneous process. On melting, ice changes to liquid, and in water, molecules are free to move around. Orderly structure of ice is destroyed and disorderly arrangement of water is increases. This order increases, leading to thereby increasing entropy. Okay, the same type of changes when entropy will increase. So increase in entropy indicates the increase in disorder or the randomness in the system. Okay, solids or crystals which have lowest entropy, whereas gases, liquid and gases will have highest entropy. For any system, such type of any system, we can say that higher the order or higher the arrangement, then less will be entropy, and higher the disorder, higher will be the entropy. In the same way, one gas diffuses into another, one liquid diffuses into another liquid, will increase the entropy because we are disturbing its order state. That is, if we consider these are liquids in which one liquid contains same molecules. If we add another liquid into it, one molecule added, then its overall order will be disturbed, then entropy will be medium. If we add more amount of another liquid, then the disorder will be increased and entropy will be increased, okay, eventually. So in similar way, high randomness, high disorder, high entropy. As we go towards the crystal or towards the higher order system, we get low randomness, low disorder, and the low entropy. From these diagrams, okay, from these pictures, you can understand what is entropy. Then further, it is used as a measure of unavailable energy. The total energy of system is made up of two parts. That is available energy to do the work, which is nothing but free energy or gives free energy, plus the unavailable energy, which is given by H is equal to G plus Ts, or change in total energy delta H, or change in heat. H is nothing but the heat energy of the system, delta G plus T delta S. The unavailable energy is represented as the product of entropy and absolute temperature T. Thus, unavailable energy is T, yes, that is T into, yes. Higher the temperature, more is the disorder and more is the unavailable energy to do the work. Thus, entropy becomes a measure of unavailable energy. For example, when heat is supplied to a solid, some of the energy is used to melt the solid. This energy is unavailable part of energy, that is entropy, and remaining energy is used to the do work. Entropy and probability. It is found that the system has a tendency to assume the most probable state. Okay, try to tend towards the system, try to go towards the most probable state. The most probable state is the most random arrangement of the molecules in the system. Hence, it means that there is a greater probability of the disordered state than the ordered state. Okay, the disordered state has highest entropy than the ordered state. That's why. For example, water in liquid form has the number of arrangements of H2O molecules, while ice has a single order arrangement. Thus, water has the higher entropy than the that of ice. Thus, we can identify the entropy as a function of probability of thermodynamic state. Now, based on that, a third law of thermodynamics is developed. Okay, each of the first three laws of thermodynamics leads to existence of state function. The zeroth law, okay, for a zero, first, second, and third law. The zeroth law leads to the temperature. First law leads to the concept of internal energy, that is E, and second law leads to the concept of entropy, yes. However, first and second laws do not give any idea about the measurements of absolute values of internal energy and entropy. Okay, absolute means within the path. Just first and second law indicates that the entropy or internal energy cannot be measured absolutely, that means within the path, but we can measure only the change in the internal energy and entropy. Determination of absolute value of energy is not feasible because it is highly difficult, and only energy changes can be determined. That means we can measure the energy or heat at initial stage and at the final stage. Okay, that's why we can measure only the change in energy and not between the path. However, the entropy concept is of great importance and its absolute value can be determined with the help of third law of thermodynamics. Richards and Nernst studied independently the entropy changes of certain isothermal chemical reactions and found that the change in entropy approaches zero as the temperature was reduced. This is true only in case of reactions where the reactants and products are perfect crystals. Experimental evidence has shown that the entropy of solutions and supercooled liquids is not zero at 0 Kelvin. For pure crystalline substances, third law has been verified repeatedly, and it was found that all pure crystals of pure substances have the same entropy at 0 Kelvin. If they have the same entropy at 0 Kelvin, this value might be taken as 0. So accordingly, the scientist Max Planck was the first to state the third law. According to the third law, the entropies of all perfectly crystalline substances are zero. Okay, so what is the statement of third law? The entropies of all perfectly crystalline substances are zero at 0 Kelvin. So absolute entropy and evaluation of absolute entropy. Let us see how we can relate this absolute entropy. Okay, it is possible to calculate absolute entropy at different or higher temperature using the method of thermochemistry. Suppose we want to determine the entropy at 298 Kelvin for certain gaseous substance. Then we can start the crystal solid of that substance as close to 0 Kelvin as possible and determine the entropy change on warming to its melting point. Okay, so accordingly, first at 0 Kelvin, that is absolute zero temperature, the gaseous, that ideal gas will be in crystal form. Okay, 0 Kelvin, that means minus 273 Kelvin. Sorry, minus 273 degrees Celsius. Okay, so as we will increase the temperature, at a certain point, which is called at its fission point, it will start to melt. Okay, at a particular temperature, we can observe that it will start to melt, and further, after melting, it will convert it into liquid. okay, converted into liquid, and then liquid again, if we start increasing temperature, it will boils, okay, it will boils at a certain temperature, and after that certain temperature it will be vaporized, okay, that means it will convert into vapor states, okay. So this we can understand through this graph, okay, from starting from the 0 Kelvin. First will be fission point. This is the temperature at melting of that crystal or the solid gas, okay, gas substance. Then at from this point it will be in liquid state. At this point it's boiling point, that is start boiling. This is the temperature where complete boiling. This line indicates the temperature is constant, that means this is boiling counter, but the entropy will increase as the number of molecules, okay. This point will be the start of boiling, okay. Up to this, the complete conversion of all molecules into vapors will take place, and in further it will be in a vapor state. The molecule will be substance will be in vapor state. Similarly, at this point, at the starting of melting, okay, this is the start point of melting, and up to this point a complete melting, okay, that is complete liquefaction of this substance will take place. The temperature will be the same, okay, temperature will be the same, that is TF, temperature of fusion, okay. Temperature of fusion, okay, but entropy will be found increasing. Accordingly, the next entropy change due to melting, accordingly we can calculate, okay, the entropy change, that is delta S at delta S1, S2, S3, S4 and S5, number of S1, S2, S3, S4 and S5, S5, all they are the different entropies as different states of the substance. Accordingly we can calculate this entropy by this using this equation. First is delta S1 is given by 0 Kelvin to the temperature of fusion temperature, integration of Cp, that is molar heat capacity at constant pressure, and dt by T, that means change in temperature. Again, the next entropy change is due to the melting of solid, okay. At this point, the delta yes, that is change in entropy will be given by this expression, whereas at this point there is delta SF, delta S2 will be given by this heat content delta HF, or heat change at fusion point at the temperature TM. Further, the liquid is then further warmed to its normal boiling point TB, and entropy change is given by similarly delta S3 will be TF to TB integration of molar heat capacity at constant pressure with the change in temperature. Now, entropy change due to vaporization of liquid will be given by delta S4 is equal to this heat content, change in heat content of vaporization to the TB, that is boiling temperature. Finally, the gas is warmed to 298 Kelvin, okay, that is 25 degrees Celsius, and delta S5, the final entropy change will be given by TB, that is boiling temperature to the 298 Kelvin, and integration of heat capacity at constant pressure with the change in temperature. The sum of all the above terms gives the entropy change, that is overall entropy change will be given by delta S is equal to S at 298 final state and the S at 0, the entropy at 0 Kelvin and entropy at 298 Kelvin, which is given by sum of all these entropy, that is S1, delta S1, delta S2 up to delta S5. Thus, this sequence is illustrated, okay, in this figure you can understand. So overall, yes, overall entropy will be given by the sum of all these entropies, all these change in entropies. Hence, we can write this equation in this way. That is, all these equations, sum of all these equation gives the entropy of substance at 298 Kelvin. Or in other way, we can say that at any temperature, entropy at any temperature, not only 298, any temperature will be given by this expression. That is, entropy change in all the steps as indicated in this diagram or in this graph, that is 0 Kelvin to the fusion temperature, then then liquid, okay, then change in enthalpy or change in heat content in the liquid state, then further this liquid liquid state to the boiling point, that is fusion point to the boiling point, then uh, and plus its heat of vaporization with the temperature, boiling temperature, and finally with the boiling temperature to the temperature, the particular temperature. It may be 298, 300, whatever may be temperature. So accordingly, we get the total entropy of the system, okay, or total entropy of substances from the 0 Kelvin to the temperature we are interested in. The value St, that is entropy at particular temperature, is always positive quantity. All the properties except entropy at 0 Kelvin can be measured calorimetrically, okay? Not the colorimetrically, it is calorimetrically. So calorimetric is the technique or instrumental technique used for the measurement of such temperature changes. The integrals can be evaluated by numerical integration or graphical, in this graphical way. In graphical method, as seen in this, the same diagram, okay, these same steps can be evaluated through continuous graph. Okay, overall graph, if we plot it, the graph will be as like this. This will be the total area, that is entropy at temperature T. This is the total area, indicates the entropy. Okay, if the area, if there are various solid forms like Sr to Sm, that is solid forms Sr and Sm, rhombohedral to monoclinic. This is one of the allotropes of, for example, allotropes of any substance like sulfur. Okay, Sr and Sm. R indicates rhombohedral structure, M indicates monoclinic structure. Corresponding entropies of transition are also to be added in the above equations. Okay, in practice, heat capacities, the Cp, are usually measured from approximately 20 Kelvin to desired temperature. At very low temperature, this 10 to 15 Kelvin, Cp values are obtained from the Debye equation. Okay, Debye equation, which is Cp is equal to A into T cube. Okay, then accordingly, we get the equation as S at particular temperature, drop at particular temperature will be given by this equation. Okay, overall A into Tf cube by the 3. And overall, we can measure this S, that is entropy, is equal to 1 by 3 Cp. Cp means the heat capacity. For perfect crystal at S0, that means at 0 Kelvin, entropies reported, there are a number of entropies that at particular that is particular temperature will be as like this for ammonia, carbon dioxide, helium. Okay, liquids like benzene, ethanol, or solids like calcium oxide, copper, calcium oxide, copper, diamond, graphite. Okay, all these are the, this table indicates, all these indicated, these are entropies. Okay, so this is about third law of thermodynamics and the entropy. Okay, so in next lecture we will see further part, that is thermochemistry part of this chemical energetic topics. Now I will stop here.